What if I told you that space itself isn't real? Well, not in the way you think it is. Look, right now, space feels solid, reliable. There's always a little more distance ahead of you, a little more time passing by. You reach for your phone, your hand crosses that space like it's nothing. Smooth, continuous, predictable. And for hundreds of years, physics agreed with you. You could divide space forever. Halves into quarters, quarters into eighths, on and on. Time, same deal. Hours into minutes, seconds into heartbeats, heartbeats into... You get it. Reality seemed smooth all the way down, like this perfect unbroken fabric that the entire universe was painted on. But here's where things get weird. And because when scientists started looking closer, and I mean really close, they found something that shattered everything we thought we knew. Down at the smallest scales imaginable, atoms and particles just stopped cooperating. The beautiful equations that explain gravity, the elegant geometry of curves and distances, they break, they completely fall apart. Distance becomes impossible to pin down, like trying to measure a shadow with a ruler made of light. Time loses its rhythm, its steady tick-tock dissolving into this bizarre probabilistic hum. And that smooth, continuous universe we learned about in school, it's a lie. Well, not exactly a lie. More like a really convincing illusion. A shortcut our brains use because the truth is too insane to process. Because way down there, in realms so small and so dense they make black holes look empty, space-time doesn't act like a stage anymore. It doesn't just sit there while events play out on top of it. No, it fluctuates. It throbs with hidden energy. It might even break apart into tiny pieces, like pixels on a screen. Or maybe, and this is the part that'll keep you up at night, maybe space only looks smooth from far away, like how the ocean looks calm from a plane, but up close, it's chaos, churning, restless, alive. Which brings us to the question, the one that scientists have been losing sleep over. When does space stop being space? At what exact point does reality, the very fabric that holds everything together, stop acting normal and start behaving like some quantum nightmare we barely understand? Stick around, because what I'm about to show you will completely change how you see the universe. Welcome. If you enjoy calm, thoughtful explorations like this, please take a moment to like this video and subscribe to the channel. It truly helps. And let me know in the comments, where are you watching from? Whether you're grounded in one familiar place or drifting quietly through space and time somewhere else, your perspective is part of this story. Space and time usually present themselves as the most stable and continuous features of experience. A room extends smoothly from one wall to another, a seamless expanse you can cross without a second thought. A path connects two places without interruption, a line drawn against the earth. A moment gives way to the next in an orderly, irreversible sequence. There is no sense that distance comes in pieces, that you move in tiny, imperceptible jumps. There is no feeling that time advances in steps like the second hand of a clock. Everything appears divisible without limit, a continuum that yields to finer and finer examination. This impression is not subtle. It is reinforced constantly by movement, by measurement, and by memory. You measure a table in meters, then centimeters, then millimeters. With better tools, a magnifying glass, a microscope, the same surface can be resolved into smaller and smaller lengths, revealing grain, texture, microscopic landscapes. No matter how closely it is examined, space appears to allow further subdivision, an infinite regress of detail. Time behaves in the same obedient way. A minute can be divided into seconds, seconds into tenths, hundredths, milliseconds, nanoseconds. The process never seems to reach a boundary, a final atom of time. We can always imagine a smaller interval because this behavior aligns so perfectly with raw experience, it shaped the earliest formal descriptions of the physical world. Classical geometry, born in ancient Greece, treated space as continuous by definition. A line had length, but no thickness. A point had position, but no size. Between any 2 points, another point could always be placed ad infinitum. These ideas were not experimental conclusions, but mathematical foundations, axioms chosen for their consistency and power. Geometry assumed continuity because it was elegant, logically robust, and, as far as anyone could tell, matched observation perfectly. When physics began to formalize motion and force, it adopted these same assumptions without question. Thus, in the late 17th century, Isaac Newton described space as absolute, infinite, and unchanging, since space existed independently of matter. an invisible rigid grid providing a fixed arena in which objects moved. Time was also absolute, a universal river flowing uniformly and identically everywhere, from your kitchen to the heart of a distant star. Events unfolded within this framework, but did not alter it. The stage remained untouched by the play. Newton's laws of motion rely entirely on this picture. Position, velocity, and acceleration are defined using the concepts of continuous space and continuous time. A body moves along a path that can be specified precisely at every infinitesimal moment. Forces act continuously, producing smooth, predictable changes in motion. And the mathematics presumes that positions and moments can be specified with arbitrary accuracy, at least in principle. There are no built-in limits to knowledge, only practical ones. This framework proved extraordinarily effective, almost magically so. At human scales, classical mechanics predicts motion with a reliability that borders on routine. Bridges remain standing because stresses can be calculated accurately. Vehicles move as expected because forces and trajectories behave predictably. The assumptions of smooth space and time introduce no detectable error in these contexts. They're invisibly perfect. The same is true far beyond everyday experience. Planetary orbits, described using Newtonian gravity, can be predicted centuries into the future with stunning precision. The positions of planets, moons, comets follow paths that are smooth, continuous, and stable over long periods, elegant ellipses against the black. Even before modern instruments, astronomers using this smooth clockwork universe could calculate eclipses and celestial alignments, their predictions confirming the continuous flow of time and space. Distances on astronomical scales reinforce the same conclusion. The average distance between Earth and the Sun is about 150 million kilometers, a vast but perfectly measurable gap. The nearest star beyond the Sun is more than 4 light-years away, roughly 40 trillion kilometers. These immense separations behave exactly as a continuous spatial framework would suggest. Light travels in predictable straight lines, or so it seemed. Objects move along smooth, calculable trajectories. No irregular structure in space, and no invisible grain interferes with these motions. Timekeeping offers a similar picture of perfect continuity. Modern atomic clocks measure time using the oscillations of atoms, achieving such precision that they lose less than 1 second over millions of years. These clocks rely on quantum processes within atoms, a hint of the strange world beneath. Yet the time they measure, the time they output to our world, behaves as a continuous flowing quantity. There is no evidence at these scales that time itself advances in discrete jumps. The second hand, whether physical or digital, sweeps smoothly. Even when our understanding of gravity was utterly reconceived in the early 20th century, continuity remained intact, woven into the new theory's heart. And Albert Einstein's theory of general relativity replaced Newton's absolute space and time with spacetime, a unified dynamic structure that wove together 3 dimensions of space with one of time into a single, malleable fabric. In this description, gravity is not a mysterious force acting mysteriously across empty space, but a manifestation of curved spacetime produced by mass and energy. A planet orbits a star not because it is being pulled, but because it is rolling along a groove in the cosmic fabric, a groove carved by the star's presence. Despite this monumental conceptual shift from force to geometry, spacetime in general relativity remains smooth. The theory assumes, as its foundation, that spacetime can be described by the continuous mathematics of differential geometry at every scale. A curvature may become extreme near massive objects, warping fiercely, but it is still defined at every point, smoothly varying from one location to the next. The equations describe how spacetime bends, stretches, and evolves without requiring any smallest unit of length or time. The fabric is infinitely divisible. This assumption of smoothness has been tested extensively, pushed to extremes. General relativity predicts the bending of starlight near the Sun, the precise precession of Mercury's orbit, the slowing of time in gravitational fields, and the existence of gravitational waves, ripples in the fabric. Observations from radio telescopes, spacecraft, and detectors like LIGO confirm these predictions with breathtaking accuracy. Across this vast range of scales, ascent from laboratory experiments to the dance of galaxies billions of light-years apart, spacetime behaves as though it is smooth and continuous. This consistency is not accidental. It reflects the fact that the underlying assumptions align perfectly with the dominant physical processes at these scales. One profound reason smoothness works so well is that most of our measurements involve large numbers of underlying interactions. Any microscopic irregularities, if they exist, are averaged out, washed away in the collective behaviour. Just as a solid wooden table appears continuous, hard and uniform despite being made of atoms separated by vast empty space and jostling with motion, space-time may appear smooth because its fine structure, if it exists, is far smaller than the scales we are probing. This idea of averaging is common, and even comforting in physics. Temperature feels like a continuous quantity, rising and falling smoothly in a room. In reality, it reflects the average kinetic energy of countless particles. At the level of individual atoms, energy changes occur in discrete, jarring jumps during collisions. Yet the aggregate behaviour is so well described by a single continuous variable, the temperature, that we forget the chaos beneath. Fluid motion offers another classic example. Water flowing in a river obeys elegant equations that treat it as a continuous, seamless medium. These equations succeed brilliantly because they describe behaviour at scales much larger than individual water molecules. At the scale of a single molecule, the concept of flow loses meaning. The description fails, but only because it is being applied outside its domain of validity. A smooth spacetime may function in the same way. It may be an effective description, a brilliant approximation that captures large-scale behaviour while remaining silent, agnostic about any finer structure. The absence of observable irregularities does not guarantee that none exist. It indicates only that they do not matter for the phenomena being described. They are hidden in the noise beyond the resolution of our inquiries. Importantly, nothing in ordinary experience forces this question into view. There are no visible gaps in space as you walk across a room. There are no missing moments in time as you wait for a sunrise. Motion proceeds continuously, and measurement refines smoothly from meters to millimeters to microns. This seamless experience is precisely why classical and relativistic descriptions have endured for so long. They describe the world as it presents itself to us across an enormous range of conditions, from the throw of a ball to the orbit of a planet. They are empirically true in their domain. However, physics does not and cannot stop at familiar scales. Its journey is one of relentless inquiry, pushing into the unknown. As investigations push towards smaller distances and higher energies, into the heart of the atom and beyond, new behaviour emerged, behaviour that shattered the smooth deterministic picture. Matter no longer followed neat, predictable trajectories. Energy appeared not as a continuous flow, but in discrete, lumpy amounts. Measurements themselves acquired fundamental, inescapable limits. Quantum mechanics revealed that continuity, so spectacularly successful at large scales, was not a universal feature of physical law. Instead, it was a special case, an emergent piece that broke down under close inspection. The recognition that matter behaves differently at small scales raises a natural, inevitable question. If particles and fields obey quantum rules, if they jump probably and defy precise location, what about the space-time they inhabit? Does space-time remain a smooth classical continuum no matter how closely we examine it, a steadfast stage even when the actors are following a wildly different script? Or does its apparent smoothness merely reflect the limits of our observation, a facade that crumbles when we look too closely? The classical picture, of course, remains essential. It captures real, measurable behaviour with remarkable accuracy. Any deeper description must recover this smoothness where it applies, and it must explain why the world feels continuous to us. The goal is not to discard the familiar framework, but to understand why it works so well and, crucially, where it might stop being the whole story. This journey from the smooth certainty of our daily experience to the fuzzy quantum edge of reality is not just about physics. It is about understanding the nature of the stage itself and whether the stage has a life of its own. The idea that space and time might be more than a passive setting marks one of the most important shifts in the history of physics. This shift is closely associated with Albert Einstein, who in the early 20th century proposed a radically different way of understanding gravity and motion. Before this change, gravity was treated as a force acting between masses across space. Objects attracted one another, and the strength of that attraction depended on their masses and separation. Space itself played no active role. It simply existed, providing distances over which forces acted, and time during which motion unfolded. It was a container, nothing more. Einstein approached the problem from a different angle, a perspective born of deep thought experiments. Instead of asking how objects move through space under the influence of gravity, he asked what space and time themselves are doing in the presence of matter and energy. What if the stage itself was flexible? The result was the theory of general relativity, published in 1915. At its core is a simple but far-reaching idea. Gravity is not a force in the traditional sense. It is a geometric effect. Mass and energy change the structure of space-time, and objects move in response to that structure. In this view, space-time is not an abstract backdrop. It is a physical entity with properties that can change, stretch, and curve. To understand this, it helps to gently separate intuition from formal mathematics. General relativity is often associated with complex tensors and equations, but the central concept can be felt without them. Space-time can curve. That curvature influences how everything moves. An object that is not being pushed or pulled by any force, a particle in free fall, follows the straightest possible path through space-time, a path called a geodesic. In flat, empty space-time, that path looks like uniform motion in a straight line. In curved space-time, the same principle applies, but the path itself is bent because the geometry is bent. This is why gravity can be understood without invoking a mysterious instantaneous pull. A planet orbiting a star is not being tugged along a curved path by an invisible string. Instead, it is following the natural, straight-line geometry of a space-time that has been shaped by the star's mass. The orbit appears curved to us because the space-time through which the planet moves is itself curved. A common, if limited, analogy involves a stretched rubber sheet with a heavy weight placed at its centre. The sheet deforms, creating a slope. A smaller marble rolled nearby will spiral inward, not because it is attracted by a force from the weight, but because it is rolling downhill on a curved surface. But while this picture has limitations, it uses gravity to explain gravity by having the weight sag in Earth's gravitational field. It captures the essential revolutionary idea: geometry directs motion. In Einstein's theory, mass and energy determine how space-time curves, and this curvature tells mass and energy how to move. This relationship is precise and quantitative, even though we are describing it qualitatively. Dense objects like stars and planets create stronger, more pronounced curvature than less massive ones. Extremely compact objects, neutron stars and black holes, produce curvature so intense, so severe, that it dramatically alters the very behaviour of space and time around them, creating traps from which not even light can escape. Importantly, it's not just mass. Energy also plays a role. Pressure, momentum, and energy density all contribute to space-time curvature. Light itself, despite having no rest mass, follows curved paths near massive objects because space-time is curved, not because light experiences a force. Light is simply following the straightest line in a bent geometry. This leads to one of the earliest and most famous confirmations of general relativity, gravitational lensing. In 1919, during a total solar eclipse, astronomers led by Arthur Eddington observed that the apparent positions of stars near the sun's edge were slightly shifted. The starlight had passed close to the sun on its way to Earth, and its path had been bent by the curvature of space-time around the sun. This effect was tiny, a deflection of about 1.75 arcseconds, but it was measurable, and it matched Einstein's predictions exactly. Catapulting him to global fame, gravitational lensing has since become a standard observational tool in astronomy. Massive objects like galaxies and clusters of galaxies act as cosmic lenses, bending light from more distant sources, producing spectacular arcs, rings, and multiple images of the same quasar. These observations confirm that space-time curvature is not a mathematical abstraction or a convenient metaphor. It has direct, observable, and beautiful consequences that we can see through our telescopes. Time is also intimately affected by this curvature. In general relativity, clocks run at different rates depending on their position in a gravitational field, a phenomenon known as gravitational time dilation. A clock closer to a massive object deeper in its gravitational well ticks more slowly than one farther away. Though this is not a mechanical defect, it is time itself flowing at a different rate. This has been confirmed through exquisitely precise experiments. Atomic clocks placed at different altitudes, one on the ground, one on a mountain or in an aircraft, show measurable differences in elapsed time. Even systems as familiar and practical as the Global Positioning System, GPS, must account for this effect. The atomic clocks aboard GPS satellites experience both special relativistic time dilation, because they are moving fast relative to the ground, and general relativistic time dilation, because they are in a weaker gravitational field farther from Earth. Without continuously correcting for these combined effects, the system's navigation errors would accumulate at a rate of about 10 kilometers per day, rendering it useless. Our daily reliance on GPS is a silent, constant testament to the reality of curved, dynamic spacetime. These confirmations establish spacetime not as a passive container, but as an active participant in physical processes. It stretches, bends, and influences motion. It is not merely where events happen, it helps determine how events unfold. Despite this dynamic, interactive role, spacetime in general relativity retains its smooth, continuous character. Curvature changes gradually from point to point. Distances and durations can still, in principle, be subdivided without limit. There is no smallest length or time built into the theory's foundations. Spacetime behaves like a flexible but perfectly continuous fabric, a fabric that can be warped and rippled but never frayed into individual threads. That this smoothness is essential to how general relativity works mathematically. The equations assume that spacetime has well-defined properties, a metric at every location, no matter how small. Curvature is described locally, meaning it can be specified in arbitrarily small regions, approaching mathematical points. The theory relies on the idea that spacetime can be examined at finer and finer scales without losing its geometric meaning. At all the scales where general relativity has been tested, from the bending of light near our Sun to the dynamics of colliding black holes billions of light years away, this assumption holds extremely well. Even the direct detection of gravitational waves confirms this picture. These waves are smooth, propagating ripples in the spacetime fabric, and stretching and compressing space by amounts tinier than the width of an atomic nucleus as they pass through Earth. Their observed behavior matches the smooth wave-like solutions of Einstein's equations with stunning fidelity. The success of general relativity reinforces the idea introduced earlier. Smooth spacetime is not a naive guess or a philosophical prejudice. It is a carefully tested, mathematically rigorous description that works across a remarkable range of conditions, from the solar system to the edges of the visible universe. At the same time, like any good theory, it contains within its own structure hints that its domain of validity may have an end. Certain solutions to Einstein's equations, when pushed to extremes, involve singularities, points or regions where curvature becomes mathematically infinite, and the smooth description breaks down completely. The centers of black holes are the most well-known examples. These singularities are not directly observable, they are hidden behind event horizons, but their mathematical presence is a clear signal that general relativity is being pushed beyond where its assumptions might apply. Infinite curvature is not considered a physical prediction so much as a flashing red light, a sign that the theory has reached its limits, that the smooth geometric model is no longer adequate. Crucially, these problematic regions arise under very specific conditions, when matter and energy are compressed into extremely small volumes, reaching densities and pressures that defy imagination. In other words, they occur at scales far, far removed from everyday experience, and in realms where the very concepts of here and now are strained. This raises a tantalizing possibility. Perhaps spacetime itself behaves differently under such extreme conditions. Perhaps the smooth continuum is a phase of spacetime, like ice is a phase of water, and under enough pressure and density, it undergoes a transition to something else entirely. Still, it is vital to emphasize what general relativity gets brilliantly right. It provides a coherent, predictive framework in which spacetime is both smooth and dynamic. It explains gravity without invoking mysterious forces acting through empty space. It unifies space and time into a single responsive structure that is shaped by, and in turn shapes, matter and energy. This view actually deepens the idea of smooth spacetime rather than undermining it. That space and time are not just continuous, they are structured, dynamic and physical. They have a geometry that matters. They participate actively in the world. Any deep theory of space-time, any attempt to go beyond Einstein, must recover this smooth geometric behavior in all the places where it has been tested. Smooth geometry is not an illusion to be discarded. It is an accurate, powerful description within its vast range of applicability. Understanding spacetime as a dynamic geometry sets the stage, however, for more challenging questions. If spacetime can bend and evolve, If it carries energy and supports waves, then it begins to resemble other physical systems, like electromagnetic fields that are known to have an underlying microscopic quantum structure. The question that follows is not whether spacetime is real or effective, it is whether the smooth geometric picture remains valid at all scales, or whether under sufficient scrutiny, under the microscope of ultimate theoretical inquiry, spacetime itself must be described using different quantum principles. For now, what matters is this. General relativity transforms spacetime from a silent absolute backdrop into an active, measurable, flexible entity. It behaves smoothly, continuously, and predictably across the universe we can observe. That success must be understood, its depth appreciated, before any attempt is made to go beyond it. Because to find where the path ends, you must first follow it as far as it can clearly go. General relativity stands as one of the most successful theories ever developed in physics, and its predictions have been tested repeatedly across many decades, in environments ranging from quiet laboratories on Earth to the most violent energetic edges of the observable universe. Wherever it has been applied within its expected domain, the domain of strong gravity and large scales, it has performed with remarkable, almost unsettling precision. At the grandest scales, the theory describes gravity as the curvature of spacetime produced by mass and energy. This elegant description accounts for the graceful motion of planets, the swirling structure of galaxies held together by dark matter halos, and the relentless expansion of the universe itself, driven by a mysterious dark energy. Observations of planetary orbits, binary star systems slowly spiraling due to gravitational wave emission, and the dynamics of entire galactic clusters all align closely, exquisitely, with the predictions woven into Einstein's equations. One of the clearest, most dramatic demonstrations of this success came in the 21st century with the direct detection of gravitational waves. These waves are ripples in the fabric of spacetime, generated by the most extreme cosmic events, the final furious inspiral and merger of black holes and neutron stars. When the LIGO detectors first sensed a gravitational wave in 2015, it wasn't just a new discovery, it was a profound confirmation of a century-old prediction. The signal, a faint chirp rising in frequency and amplitude, matched the waveform predicted by the general relativity's simulations of black hole mergers with striking accuracy. The timing, the amplitude, and the ring-down of the final black hole, every detail provided strong evidence that spacetime behaves exactly as the theory describes, even under conditions of unimaginable violence where gravity is at its strongest. General relativity also performs exceptionally well in environments dominated by intense gravitational fields. Neutron stars, for example, are among the densest objects in the universe. A typical neutron star contains more mass than our entire Sun, compressed into a sphere barely 20 kilometers across, the size of a small city. The gravitational field at its surface is billions of times stronger than Earth's. Matter is crushed into exotic states, and spacetime is curved into a tight, deep well. Despite this, general relativity successfully describes the structure, stability, and gravitational influence of these objects. Their precise masses and radii inferred from observations of pulsars and binary systems are consistent with the equations of state and spacetime geometry the theory provides. Black holes provide an even more extreme test. These objects form when the cores of massive stars collapse catastrophically under their own gravity, compressing matter to such an extreme degree that not even light can escape from within a certain boundary known as the event horizon. The existence of black holes was once a speculative, almost philosophical possibility at the edge of theoretical physics. Today it is supported by multiple independent lines of evidence. The frantic orbits of stars around the invisible, massive object at the center of our galaxy, the high-energy radiation from superheated matter in accretion disks, and now, the direct imaging of a black hole's shadow by the Event Horizon Telescope. The mathematical description of black holes within general relativity traces back to Carl Schwarzschild, who in 1916, mere months after Einstein published his theory, discovered an exact solution to the equations describing the spacetime around a spherical non-rotating mass. This solution revealed the presence of the event horizon, a one-way boundary, and deeper still, a singularity at the center. At the event horizon itself, space-time curvature becomes extremely strong, but remains finite and well-defined. An observer falling through the boundary would not experience anything locally unusual at the precise moment of crossing, their watch would tick normally, at least initially. From the perspective of a distant observer, however, her time for the falling object appears to slow dramatically, freezing asymptotically at the horizon. These bizarre effects have been confirmed indirectly through observations of matter spiraling into black holes, and most directly through the gravitational wave signals from black hole mergers, which tell us about the properties of the horizons themselves. Up to this point, right up to the edge of the event horizon, general relativity remains internally consistent and observationally triumphant. Problems arise only when theoretical attention turns relentlessly inward to the singularity itself. A singularity is not a place of extreme conditions, it is a region where the mathematical description itself fails, where quantities like spacetime curvature or density become infinite. In the Schwarzschild solution, the singularity lies at the geometric center of the black hole, point where the equations predict that density and curvature diverge without bound. Similar singularities appear when we run the cosmic film backward in time, in models of the early universe. Extrapolating the equations of an expanding universe backward leads to a state of infinite density and temperature, a point often associated with the beginning of cosmic expansion in the classical Big Bang model. These infinities are not merely very large numbers, they are mathematical pathologies. At a singularity, physical quantities lose their meaning. Distances shrink to zero. Time ceases to behave in a well-defined way. The theory no longer provides sensible predictions, it offers a blank screen of meaningless symbols. Importantly, the singularities are not considered physical objects in the same way planets or stars are. They are better understood as glaring warning signs, bright flags planted in the equations by the theory itself. They indicate that the assumptions underlying the theory, the assumption of a smooth, continuous spacetime geometry, are being pushed beyond their breaking point. This distinction matters. General relativity does not fail gradually as conditions become more extreme. It remains accurate and predictive right up to the very edge of these singular regions. Only when curvature and density reach these extraordinary mathematically singular levels does the description collapse into nonsense. This suggests powerfully that the theory is not wrong but incomplete. Its incompleteness becomes starkly and unavoidably clearer when we bring quantum effects into consideration. Neutron stars and black holes involve matter compressed into volumes of fantastic smallness. At sufficiently high densities, the quantum properties of matter cannot be ignored. Electrons, neutrons, and quarks obey quantum rules that impose fundamental limits on how closely they can be packed together. These quantum effects, like the Pauli exclusion principle, which gives rise to electron degeneracy pressure, are essential to preventing many stars from collapsing further. It is quantum pressure that supports a white dwarf against gravity. In a neutron star, it is the quantum degeneracy pressure of neutrons that fights a desperate losing battle against immense gravity. General relativity, however, treats matter in a largely classical, smooth way, and it does not include the fundamental quantum behavior of particles at its core. This omission is not problematic at low densities or large scales, where quantum details average out. But it becomes critical, even fatal, when matter is compressed into the extreme states that lead to singularities. The same profound issue applies to spacetime itself. General relativity assumes that spacetime can be described as a smooth continuum down to arbitrarily small scales, infinitely divisible. Quantum mechanics, by contrast, introduces fundamental, inescapable limits on measurement and precision. When energy is confined to very small regions, quantum fluctuations become significant, even dominant. Attempting to probe spacetime at extremely small distances requires concentrating tremendous energy into a tiny volume, which in turn, according to general relativity itself, would strongly disturb, warp and curve the very spacetime being measured. This is a profound tension, a circular puzzle. To see the fine structure of spacetime, you must hit it with immense energy, but doing so destroys the geometry you're trying to measure. This tension suggests that singularities arise not because spacetime truly becomes infinite or ill-defined in reality, but because the theory describing it is being used outside its domain of validity. The smooth geometric picture works exceptionally well until it encounters regimes where quantum effects cannot be ignored, where the stage itself must be subject to the same quantum rules as the actors upon it. Evidence for this limitation also appears in cosmology, in our very origin story. When the equations of general relativity are applied to the universe as a whole, they describe an expanding spacetime that was denser, hotter, and smaller in the past. Extrapolating this expansion backward leads to a state of extreme density and temperature, a cosmic singularity, the Big Bang. Yet this extrapolation assumes, implicitly, that classical spacetime remains valid all the way back, at the earliest times, when the universe was smaller than a subatomic particle and energies were beyond anything we can create. Quantum effects would have been unavoidable, overwhelming. The appearance of a singularity in this context, again, is less a physical prediction and more a signal, a blinking sign that reads, "Classical description breaks down here." It is worth emphasizing strongly that these issues do not undermine the monumental successes of general relativity. The theory remains the best, the only, available description of gravity and spacetime at macroscopic scales. Its predictions continue to be confirmed with ever-increasing precision. The problems arise only when the theory is extended, courageously or naively, into regimes it was never designed to handle, regimes where quantum physics must hold sway. In this sense, singularities serve a constructive, almost guiding role. They highlight the precise points at which new physics is required. They indicate where a more complete framework must take over, one that incorporates both the geometric insights of general relativity and the probabilistic discrete structure of quantum mechanics. The existence of these limits motivates the search for a deeper theory, and not because general relativity fails broadly, but precisely because it succeeds so completely, so beautifully within a well-defined range. Understanding where and why it stops working provides the sharpest clues about the underlying structure of spacetime itself. The picture that emerges is one of layered description. Smooth spacetime geometry governs the large-scale behavior of the universe. It explains gravity, motion, and cosmic structure with breathtaking accuracy. But at extreme densities and unimaginably small scales, the assumptions that support this picture may no longer hold. The smooth fabric might fray. Recognizing both the towering success and the clear signaled limits of general relativity sets the stage for the next step, the introduction of the other great pillar of 20th century physics. And if smooth spacetime breaks down only under the most extreme conditions, then the question becomes precise rather than speculative. At what scale do those conditions arise, and what replaces the classical description when they do? The cracks in smooth spacetime do not appear everywhere. They appear only where nature is pushed to its extremes, in the hearts of black holes and the first instance of the cosmos. That fact narrows the problem and gives it direction. It tells us where to look, even if we cannot look directly. As the limits of classical spacetime become visible under extreme conditions, a very different framework enters the picture. This framework was not developed to explain gravity or cosmic structure, but to understand how nature behaves at the very smallest scales we could probe. It is known as quantum mechanics, and it describes a world that does not behave smoothly or continuously in any way the classical physics of Newton or Einstein would recognize. Quantum mechanics emerged not from philosophical speculation, but from the stubborn, repeated failure of classical physics in the face of precise experiment. At the beginning of the 20th century, classical theory could not explain how atoms emit light in discrete spectra, how energy is exchanged in the photoelectric effect, or why matter remains stable at all. Predictions disagreed with observations in precise, repeatable, and embarrassing ways. Something fundamental was missing from the smooth, deterministic picture. One of the first clear signs appeared in the study of heat and radiation, and in the problem of black body radiation. When physicists examined how hot objects, like a glowing piece of metal, emit light, classical theory predicted that energy should be released continuously across all frequencies, leading to an absurd result: infinite energy output in the ultraviolet. This was the ultraviolet catastrophe, and it was not a subtle discrepancy. The equations simply did not work. They described a reality that did not exist. In 1900, Max Planck proposed a radical, almost desperate solution. He suggested that energy is not exchanged continuously, like a flowing fluid, but in discrete lumpy amounts, which he called quanta. These amounts depended on the frequency of the radiation, and were set by a new fundamental constant of nature, hh, now called Planck's constant. Energy, according to this proposal, came in packets rather than flowing in a smooth stream. This idea of quantization was initially introduced as a mathematical fix, a trick to make the equations fit the data. Planck himself was cautious, even skeptical about its physical implications. However, the results matched experimental data precisely. What had seemed like a technical adjustment turned out to reflect a deep fundamental feature of nature. Over the following decades, this principle appeared again and again, inescapable. Albert Einstein, in 1905, applied it to explain the photoelectric effect, showing that light itself behaves as if it consists of discrete energy units, particles of light later called photons. Niels Bohr used quantization to describe atomic structure, proposing that electrons occupy specific discrete energy levels around a nucleus, that rather than moving in any possible orbit, they could jump between these levels by absorbing or emitting a photon of precise energy, explaining the sharp lines in atomic spectra. Experiments confirm that atoms absorb and emit energy only in specific amounts, not in a continuous range. These discoveries revealed a sharp fundamental contrast with classical motion. In classical physics, a particle can have any energy value and follow a smooth, deterministic trajectory through space. In quantum mechanics, certain quantities are restricted, quantized. Energy levels are like rungs on a ladder. You can be on one rung or another, but not in between. Transitions occur in instantaneous jumps rather than gradual smooth changes. This discreteness does not mean that everything is made of tiny hard blocks in a simple Lego-like sense. Instead, it reflects fundamental limits on what can be measured and how systems can behave. The mathematical structure of quantum mechanics describes probabilities rather than definite outcomes. It predicts the likelihood of finding a particle in a particular place or state, not a single precise result. The world at its root is not deterministic, but probabilistic. One of the most profound consequences of this framework is the principle of uncertainty, formulated by Werner Heisenberg. He showed that certain pairs of physical quantities cannot both be known with arbitrary precision at the same time. Position and momentum are the key example. The more precisely you pin down a particle's position, the less precisely you can know its momentum and vice versa. This uncertainty is not a flaw in our measurement techniques. It's not a matter of clumsy tools. It is a fundamental, inescapable feature of nature as described by quantum mechanics. No improvement in instruments, no advancement in technology can ever remove it. The limitation arises from the wave-like nature of quantum objects and how physical quantities are mathematically defined within the theory. As a result, the entire classical idea of a particle following a well-defined path through space loses its meaning at small scales. Between measurements, a quantum particle does not occupy a single trajectory. Instead, it is described by a distribution of possible positions and momenta, a wave function that encodes probabilities. Classical motion, with its smooth, certain paths, emerges only when these probability distributions are narrow enough, due to averaging over many particles or large masses, so to approximate a single definite line. Probability replaces certainty at the most basic level of description. This does not mean quantum mechanics is vague or imprecise. On the contrary, its predictions are often extraordinarily, almost miraculously accurate. What changes is the type of prediction being made. Instead of specifying exact outcomes, the theory specifies probabilities with well-defined, calculable mathematical rules. This shift has profound implications for how we describe reality. In classical physics, systems have properties whether or not they are observed. The moon is there even when no one looks. In quantum mechanics, the act of measurement plays a central puzzling role. Observables such as position, energy, and spin acquire definite classical values only when measured. This is a process that remains the subject of deep interpretation and debate. These ideas can seem abstract, counterintuitive, even unsettling, but they have direct, irrefutable experimental support. Interference experiments with electrons, and even large molecules, show patterns that can only be explained by wave-like probability distributions passing through two slits at once. Precision measurements of atomic spectra confirm discrete energy levels with astonishing consistency. Technologies that define our modern world, lasers, semiconductors, MRI machines, and atomic clocks, rely fundamentally on quantum principles and function exactly as the theory predicts. Despite its counterintuitive aspects, quantum mechanics is not optional. It is the correct description of nature at small scales. Any theory that ignores it fails to account for a vast and foundational range of observed phenomena. The contrast with classical physics is therefore stark, even jarring. Classical theories describe a smooth change and continuous motion and precise trajectories. Quantum mechanics describes discrete outcomes, probabilistic behavior, and fundamental limits on measurement. The two frameworks are not merely different in detail. They rest on different, seemingly contradictory assumptions about how physical quantities exist and how they can be known. This difference becomes especially critical when scale is considered. At large, human scales, quantum effects average out. The probabilistic behavior of countless particles, like the random motions of molecules in a gas, produces stable, predictable, collective outcomes like pressure and temperature. But this is why classical physics works so brilliantly for everyday objects. Baseballs, rockets, planets. The underlying quantum structure does not disappear, but it becomes irrelevant to most practical questions. It is hidden in the noise. At small scales, however, the quantum description is unavoidable, dominant. Atoms, electrons, and photons do not and cannot behave classically. Their properties are quantized. Their behavior is governed by probability rather than certainty. Attempts to force classical concepts onto these systems lead immediately to contradictions and failed predictions. This raises the critical, unavoidable issue when we finally consider gravity and spacetime together. General relativity describes spacetime as smooth, continuous, and deterministic, a classical geometric object. Quantum mechanics describes matter and energy as discrete, probabilistic, and subject to fundamental uncertainty. Both theories are supported by overwhelming experimental evidence. Both work extremely well in their respective domains that together cover almost all of the known physics. The profound difficulty arises because the two frameworks make incompatible, perhaps irreconcilable assumptions about the world. Quantum mechanics, in its standard formulation, assumes a fixed, unchanging background of space and time in which particles and fields exist and evolve. General relativity treats space-time itself as dynamic, as the very thing that is shaped by energy and momentum. Quantum mechanics introduces uncertainty and quantization at small scales. General relativity assumes that spacetime can be subdivided without limit, remaining smooth. When gravity is weak and scales are large, this tension can be safely ignored. Quantum effects are negligible, and spacetime behaves classically. When quantum effects dominate but gravity is weak, as in a particle accelerator, spacetime can be treated as a fixed, flat background. The real problems appear only when both gravity and quantum effects are strong at the same time. These conditions occur when matter and energy are confined to extremely small regions, where their density makes gravity powerful and their scale makes quantum behavior dominant. They are relevant near the singularities inside black holes, at the very beginning of cosmic expansion, and potentially at scales far, far beyond the reach of any conceivable experiment. In these regimes, neither classical spacetime nor standard quantum mechanics can be applied without modification. Each theory, pushed alone into this territory, breaks down. The appearance of quantum mechanics in our story therefore marks a fundamental turning point. It introduces a description of physical reality that challenges the smooth spacetime assumption at its core. It does not merely add new details to an existing framework. It changes the foundational rules by which physical quantities are defined and related. Understanding this contrast is essential. The question of when spacetime becomes quantum is not about casually replacing one theory with another. It is about identifying where the assumptions of each theory cease to apply and how they might be reconciled in a single, coherent description of nature. The quantum world does not deny the success of classical descriptions. It explains why they work where they do. At the same time, it sets clear fundamental boundaries. Beyond those boundaries, continuity, determinism, and smooth geometry can no longer be taken for granted. This is the tension that now comes into sharp focus. A theory built on the smooth dynamic geometry of spacetime meets a theory built on quantization, probability, and uncertainty. The point at which these two descriptions intersect, where both gravity and quantum effects are paramount, is where the question of quantum spacetime becomes not just interesting, but unavoidable. It is the next great frontier of fundamental physics. Once both general relativity and quantum mechanics are placed side by side, a deeper, more fundamental problem becomes impossible to ignore. And each theory is extraordinarily successful, even triumphant within its own domain. Yet when their assumptions are combined, when we try to make them speak to each other about the same region of reality, they resist fitting together into a single coherent description. The disagreement is not about minor experimental details or approximations. It runs through the very foundations of how each theory understands reality. At the heart of the issue is how each framework treats the concepts of space and time. In quantum mechanics, space and time are treated as a fixed, unchanging background. Particles and fields exist within this background. Their properties change with time. Their positions are measured within space, but the structure of space and time themselves is assumed to be stable, given, and unaffected by the quantum processes unfolding within it. The background does not respond to what happens inside it. This assumption is known as background dependence. The geometry of spacetime is specified in advance, like the immutable grid of graph paper, and remains perfectly flat and unaffected by the quantum drama scribbled upon it. This approach works extremely well when gravity is negligible, or when spacetime curvature is tiny, such as in particle physics experiments on Earth. General relativity takes the opposite, radical stance. It is fundamentally background independent. There is no fixed spacetime stage. Instead, spacetime itself is a dynamic entity whose geometry is determined by the distribution of mass and energy. In John Wheeler's famous summary, matter tells spacetime how to curve, and spacetime tells matter how to move. Geometry and dynamics are inseparable. The stage and the actors are in a constant intimate dialogue. This profound difference alone creates immense tension. Quantum mechanics requires a stable, predefined framework in which probabilities can evolve smoothly and predictably. General relativity denies the existence of such a fixed framework. When spacetime itself is subject to quantum change, the basic structure required by quantum theory, a reliable clock and ruler, becomes unstable, fluctuating. How can you calculate probabilities for events if the very arena in which before and after are defined is itself probabilistic? The conflict deepens dramatically when attempts are made to treat gravity itself using quantum methods. In quantum mechanics, forces are described by quantum fields. And these fields fluctuate. They exchange energy in discrete packets called virtual particles. Calculations involve summing over many possible interactions, each contributing to the final probability of an outcome. This approach, known as quantum field theory, has been spectacularly successful for the electromagnetic force and the nuclear forces. When the same techniques are applied to gravity, serious, seemingly insurmountable problems arise. Gravity is not just another force, it is associated with space-time curvature. Attempting to quantize gravity means treating small fluctuations in space-time geometry as quantum excitations. Imagine tiny probabilistic ripples in the fabric itself. In principle, this sounds reasonable. Gravity should have its own quantum particle, the graviton, analogous to the photon. In practice, the calculations produce infinities that cannot be removed or controlled. These are not minor technical issues, they appear at almost every step. Quantities that should correspond to measurable physical effects diverge to infinite values, rendering the theory useless for prediction. The standard mathematical tricks used to tame infinities in other quantum field theories, a process called renormalization, fail utterly in this context. The theory of quantum gravity in this naive approach is non-normalizable. This problem became starkly clear in the mid-20th century when physicists like Richard Feynman began exploring quantum gravity seriously. Feynman, who played a central role in developing quantum electrodynamics, examined whether similar diagrammatic techniques could be applied to gravity. His conclusion was cautious and telling. While it was possible to define a quantum version of gravity at low energies, the theory became unmanageable, violently ill-behaved at higher energies. The mathematical structure broke down. The underlying reason is tied to the unique nature of how gravity couples to energy. In general relativity, all forms of energy contribute to spacetime curvature. This includes not only mass and motion but also the energy of quantum fluctuations themselves. As calculations attempt to include smaller and smaller scales, which require higher and higher energies in the virtual particles, the energy associated with these fluctuations grows. The gravitational response to that energy then feeds back into the calculation, producing ever larger, more divergent contributions. It is a runaway, self-destructive feedback loop. Attempts to probe spacetime at extremely small distances require high energies. Those energies via gravity strongly distort the very spacetime being probed. The more precisely you try to examine the geometry, the less well-defined it becomes because your probe violently warps it. The mathematical expressions reflect this instability by blowing up to infinity. This behavior is fundamentally different from what occurs in other quantum theories. In quantum electrodynamics, infinities appear but can be systematically absorbed into a finite number of physical parameters, like mass and charge, through renormalization. The theory remains predictive because only a limited set of quantities need adjustment. Quantum gravity does not cooperate. New worse infinities appear at every level of approximation. There is no finite set of parameters that can absorb them all. Predictive power is completely lost. This failure is not merely technical, it reflects a deeper conceptual mismatch. Quantum mechanics assumes that uncertainties apply to physical quantities defined within spacetime. General relativity treats spacetime itself as a physical quantity. Combining these ideas implies that spacetime geometry should itself be subject to quantum uncertainty. Distances and durations would fluctuate. The notion of a sharply defined spacetime geometry, a smooth manifold, would lose its meaning at small scales. Yet quantum mechanics in its standard formulation relies on a precise notion of time to describe how systems evolve. Probabilities change with time. Quantum states are compared at different moments. If time itself becomes fuzzy and uncertain, then the standard formulation of quantum theory begins to unravel. This creates a profound circular dependency. Quantum mechanics needs a stable spacetime to function. General relativity predicts that spacetime responds dynamically to energy, including the energy of quantum fluctuations. Each theory, when pushed into this overlapping domain, undermines the assumptions of the other. The disagreement also appears in how each theory treats locality. Quantum field theories assume that interactions occur at specific points in spacetime. General relativity allows spacetime itself to be curved in such a way that the notion of global simultaneity, a universal now, disappears. There is no preferred way to slice the universe into moments. This complicates, perhaps fatally, the definition of quantum states that are supposed to evolve uniformly across space. Despite these severe issues, it is crucial to be clear about what is not happening. There is no experimental contradiction between quantum mechanics and general relativity in any regime where both have been separately tested. The problem is purely theoretical, arising at the frontier of extrapolation. In most laboratory experiments, gravity is so weak, compared to other forces, that it can be completely ignored. In most astronomical contexts, quantum effects average out to such a degree that they are irrelevant. This wide separation of scales allows both theories to coexist peacefully without conflict in our current empirical experience. In practice, the profound difficulty appears only when scale is pushed to theoretical extremes, near black hole singularities, at the earliest moments of cosmic expansion, or when attempting to describe spacetime itself at distances far, far smaller than anything currently accessible to experiment. In these regimes, neither theory can be safely applied alone. General relativity predicts conditions where a spacetime curvature becomes infinite, a sign of its own breakdown. Quantum mechanics predicts fluctuations that cannot be ignored, and that would destroy any classical geometry. Each theory in its own way signals that its foundational assumptions are being violated. This is why the question of quantum spacetime remains the great unresolved problem of fundamental physics. It is not due to a lack of effort or imagination, since it arises because the foundational principles of the two most successful theories in physics pull in opposite, seemingly irreconcilable directions. One framework treats spacetime as a smooth deterministic geometry. The other treats physical quantities as probabilistic and quantized. When spacetime itself is included among those quantities, the entire mathematical and conceptual structure becomes unstable. This instability points toward an important humbling conclusion. The problem is not that one theory is correct and the other is wrong. Both are demonstrably correct within their vast separate domains. The problem is that neither is complete. Resolving this disagreement likely requires a new overarching framework that reduces to general relativity at large scales and reduces to quantum mechanics at small scales, and while providing a consistent picture in the middle where they overlap. Such a framework would need to explain how smooth spacetime emerges from a deeper quantum description and why quantum effects become negligible in ordinary conditions. Until such a framework is found and experimentally verified, the conflict remains a guide rather than a failure. It marks the boundary between what is well understood and what is not. The disagreement between quantum mechanics and gravity is therefore not a flaw in physics, it is a signal. It points to scale as the deciding factor and suggests that the very nature of spacetime depends on how closely it is examined. When fundamental disagreements appear between successful physical theories, the cause is often not location, material, or environment, but scale. The same object can behave in entirely different ways depending on the resolution of your observation. Physics does not offer a single monolithic description that applies unchanged at all distances and energies. Instead, it provides a series of effective theories, layers of description, each exquisitely suited to a particular range of scale. This idea is familiar even outside of physics. A coastline looks smooth, a simple curve when seen from a high altitude. From closer up, it becomes jagged, with bays and headlands. At the scale of individual rocks and grains of sand, the idea of a smooth line stops being useful altogether. The coastline's length becomes infinitely long depending on the size of your ruler. The object has not changed. Only the scale of observation has. Physical laws behave in much the same way. At human scales, our objects obey classical mechanics. Motion appears continuous. Forces produce smooth acceleration. Space and time behave as stable, unchanging backgrounds. These assumptions work because the relevant scales are large compared to the microscopic structure of matter and energy. The quantum graininess is invisible. At atomic scales, the picture changes completely. Electrons do not orbit nuclei like small planets. Energy levels become discrete. Probabilities replace definite trajectories. Quantum mechanics becomes essential, not because classical physics is wrong, but because it averages over details that now matter dominantly. At even larger scales, such as those of stars, galaxies, and the universe as a whole, gravity dominates. General relativity provides the appropriate description. Space-time curvature governs motion. Time flows at different rates depending on gravitational potential. Quantum effects remain present, but they are negligible because they average out across vast numbers of particles. Each of these descriptions is accurate and indispensable within its range. Problems arise only when a description is pushed beyond the scale where its assumptions hold. This perspective beautifully reframes the question of quantum spacetime. The issue is not where spacetime becomes quantum in the sense of a particular place or region. It is when, meaning at what scale, the smooth geometric description ceases to be sufficient. To make this concrete, consider the staggering range of scales involved. An atom is roughly 1/10 billionth of a meter across. A human being spans about 1 meter. Earth's diameter is roughly 12 million meters. And the observable universe stretches for tens of billions of light years, each light year being nearly 10 trillion kilometers. These scales differ by more than 40 orders of magnitude. It would be astonishing, even unreasonable, to expect the same simple description to apply unchanged across this entire mind-boggling range. Physics has long recognized this and built sophisticated methods to manage it. One such method is the formal idea of effective theories. An effective theory describes phenomena at a particular scale without attempting to capture all underlying details. It works because those details do not significantly influence the behavior being studied at that scale. Classical mechanics is a prime example of an effective theory. It ignores atomic structure and quantum uncertainty, yet it accurately predicts the motion of cars, planets, and spacecraft. Fluid dynamics is another effective theory. It treats liquids as continuous substances, even though they are made of discrete molecules. The theory succeeds because molecular details average out at the scale of a flowing river or a rising plume of smoke. Smooth spacetime, then, may be an effective description in precisely the same sense. At all scales accessible to our direct observation and experiment, from millimeters to gigaparsecs, spacetime behaves as a continuous geometric structure. Curvature changes gradually. Distances and durations can be measured with ever-increasing precision. The mathematics of general relativity works because it captures the dominant collective behavior at those scales. If spacetime has a more fundamental, possibly discrete or chaotic structure at extremely small distances, that structure may be completely irrelevant to most physical processes we care about, just as the graininess of matter does not affect the flight of a baseball. The graininess of spacetime would not affect the orbit of a planet or the propagation of a gravitational wave until you look incredibly closely. This idea is closely connected to the concept of renormalization in quantum field theory, a powerful set of techniques that formalizes how physical behavior changes with scale. Renormalization provides a mathematical framework for the notion that different descriptions apply at different resolutions. As one zooms out from small scales to large ones, certain microscopic details fade away while collective large-scale properties become dominant. In this framework, parameters like mass, charge, and interaction strength are not absolute constants. They depend on the energy scale, and thus the distance scale, at which they are measured. The fundamental laws may not change, but their effective expression does. What matters at one scale may be negligible, or integrated out at another. Applied to spacetime, this suggests a profound possibility. The smooth geometry described by general relativity may emerge from a more complex, possibly non-geometric, underlying description when viewed at large scales. At smaller scales, new degrees of freedom may become relevant, altering how spacetime behaves. Emergence is not a speculative or mystical concept. It is a well-established feature of countless physical systems. Temperature emerges from the chaotic motion of molecules. Pressure emerges from countless particle collisions. The rigidity of a solid emerges from atomic bonds and quantum forces. None of these properties, temperature, pressure, rigidity, exist at the level of individual electrons or quarks, yet they are utterly real, measurable, and govern physics at our scale. Spacetime smoothness could be similar. It may not be fundamental. It may be a large-scale property that arises when myriad microscopic details are averaged over, when the underlying quantum atoms of geometry are so numerous that their individual discreteness is invisible. This perspective helps clarify why general relativity works so spectacularly well. It is not necessarily because spacetime is fundamentally smooth at all scales, but because the smooth description captures the relevant physics at the scales where all our measurements are made. The theory is accurate because it is applied precisely where it is valid. It also explains elegantly why problems appear only under the most extreme conditions. Singularities arise when matter and energy are compressed into volumes so small that the averaging process breaks down. The microscopic details can no longer be ignored. Quantum fluctuations become significant when distances shrink to the point where the collective smooth picture is no longer a good approximation. These are precisely the regimes where scale matters most and where effective descriptions are most likely to fail. Seen this way, the epic disagreement between quantum mechanics and general relativity is not mysterious or paradoxical. Each theory is a brilliantly successful effective description tailored to a different scale. Quantum mechanics governs small systems where fluctuations and discreteness are dominant. General relativity governs large systems where collective geometry and smooth curvature are dominant. The difficulty arises in the narrow, exotic overlap where both effects are equally important, where the energy is so high, quantum, that it creates strong gravity, relativity. This overlap, while tiny in terms of scale, is crucial. It includes the conditions near black hole singularities, the earliest moments of the Big Bang, and any theoretical attempt to probe spacetime at the absolute limit of smallness. In these regimes, neither classical geometry nor standard quantum theory can be applied without qualification. A more fundamental theory is needed. Framing the problem in terms of scale also helps avoid a common misconception, that the question is not whether spacetime is quantum here and classical there in space. It is not about particular locations in the universe, it is about resolution. The same region of space, say the empty space in front of you, can appear perfectly smooth and continuous when examined with a ruler, a laser, or even a particle accelerator. But if you could hypothetically probe it at a resolution a trillion times finer, it might reveal a frothy, fluctuating, or discrete structure. The object, spacetime, has not changed, your descriptive framework has. The same is true of a wooden table. It looks solid from a distance, reveals a fibrous structure under a microscope, and appears as a cloud of quantum probability fields in empty space to a particle physicist. This may be true of spacetime itself, and if its quantum nature only becomes apparent at scales far smaller than anything currently accessible, then its quantum behavior would not contradict everyday experience or astronomical observation. It would simply lie beyond the resolution of our existing measurements. This does not diminish the importance of the question, it sharpens it. Instead of asking where spacetime changes, the focus shifts to how small one must look before the smooth description breaks down. Understanding scale as the key variable allows the problem to be posed with precision. It also prepares the ground for the introduction of the most famous fundamental limit in all of theoretical physics, the Planck scale. If there is a smallest meaningful length or time, that limit would define the scale at which spacetime's effective smoothness definitively ends. The search for that scale is not about finding a hidden boundary in space, it is about identifying the point at which our current descriptions must give way to something deeper, where the smooth fabric of reality might finally reveal its threads. As our attention moves conceptually towards smaller and smaller scales, probing the depths where smooth space-time might fray, one particular length keeps appearing in the equations of theoretical physics. It is not derived from direct measurement or experiment, but emerges naturally from the basic constants that govern nature. This length is known as the Planck length, and it plays a central, almost mythical role in all discussions about quantum spacetime. The Planck length is named after Max Planck, who, in addition to pioneering quantum theory, was interested in identifying fundamental natural units, quantities that do not depend on human conventions like meters or seconds, but instead arise directly from the deep structure of physical law. To construct such units, Planck combined the fundamental constants that appear in both quantum mechanics and gravity. One constant, h, Planck's constant, sets the scale of quantum effects. Another, gg, Newton's gravitational constant, governs the strength of gravity. A third, cc, the speed of light, links space and time through the absolute speed limit of relativity. When these constants are combined in a specific way, the result is a length scale. That length is almost inconceivably small. The Planck length is approximately 1.616 times 10 to the power of minus 35 1.616 times 10 to the power of minus 35 meters. Compared to everyday distances, yes, it is unimaginably tiny. For context, an atom is about 10 to the power of minus 1010 to the power of minus 10 meters across. A proton is roughly 10 to the power of minus 1510 to the power of minus 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. There are as many Planck lengths in a single proton as there are protons in the entire observable universe. This scale is not just small, it is utterly remote from any direct human experience or current technological reach. Despite its extreme smallness, the Planck length is not an arbitrary number. It marks the unique scale at which quantum mechanics and gravity are expected to become equally important, where their effects are of the same order of magnitude. At larger distances, gravity governs large-scale cosmic structure, but at atomic scales, it is fantastically weak compared to other forces. Conversely, quantum mechanics governs behavior at atomic scales, while gravity becomes negligible. The Planck length sits precisely at the intersection of these two regimes. It is the scale at which attempts to localize energy strongly enough to probe smaller distances would inevitably produce gravitational effects so strong that they distort spacetime itself. This is not a matter of technological limitation, it is a fundamental consequence of the laws as we know them. To measure a very small distance, you need a probe with a very short wavelength. In quantum mechanics, short wavelength means high energy, as with a high-energy photon or particle. As the energy of your probe increases, so does its gravitational influence, since energy is equivalent to mass E equals mc squared, E equals mc squared. At the Planck scale, concentrating enough energy into a region of that size to see it would cause the region to collapse into a tiny black hole. A Planck-scale black hole? At that point, the probe itself destroys the geometry it is trying to measure, and information about smaller distances becomes permanently trapped behind a horizon. The Planck length emerges as the scale where this transition occurs, the scale where measurement disrupts spacetime so severely that the classical concept of distance loses its clear operational meaning. It is no longer physically meaningful, even in principle, to speak of 2 points being separated by a distance smaller than the Planck length, because no measurement could ever confirm it without creating a black hole that hides the answer. This is why the Planck length is often described as a minimum measurable length. Then that phrase requires careful interpretation. It does not necessarily mean that space-time is literally made of discrete, indivisible chunks of that size, like pixels on a screen. Rather, it indicates that the usual procedures for defining and measuring distance, the foundation of geometry, cease to function in any familiar way. Operational meaning is paramount in physics. A quantity is considered physically meaningful only if there is, at least in principle, a way to measure it. If no conceivable experiment can distinguish between a distance of 10 to 35 meters and 10 to 36 meters, then that mathematical distinction may not correspond to anything real in the physical world. A distance is smaller than the Planck length. A no known measurement process can resolve structure without invoking energies that destroy the very notion of a stable spacetime geometry. This suggests that talking about smaller than Planck distances may be physically meaningless, even if our equations might allow us to write down such numbers. This represents a profound shift in perspective. Classical geometry assumes that distance can always be subdivided further, ad infinitum. Quantum mechanics challenges this by introducing fundamental uncertainty. Gravity reinforces the challenge by making space-time itself dynamic and sensitive to energy. Together, these effects imply a fundamental limit to the applicability of the smooth, infinitely divisible picture. It is important to be precise about what this limit does and does not say. The Planck length is not a boundary that has been observed. No experiment has directly probed distances anywhere near this scale. Our most powerful particle accelerators probe distances about 10 to the power of 15 times larger. It is a theoretical construct, a scale derived from combining well-established constants. Its significance lies in what it tells us about consistency. If both quantum mechanics and general relativity are correct within their respective domains, then there must be a scale at which neither can be applied independently. Their effects become comparable. The Planck length identifies that scale. This is why it appears repeatedly in all serious discussions of quantum gravity. It sets the point at which the smooth classical description of spacetime provided by general relativity is expected to fail, not gradually, but structurally. Above the Planck length, spacetime behaves in a way that can be approximated as continuous. Below it, the assumptions underlying continuity, the idea of a point, a line, a smooth manifold, may no longer hold. The theory does not tell us what replaces smooth geometry. It only tells us that smooth geometry cannot be assumed to continue indefinitely. Some approaches to quantum gravity suggest spacetime may become discrete at this scale, with areas and volumes taking on quantized values. Others suggest spacetime may be fundamentally relational, with geometry emerging from more basic, non-geometric interactions. Still others propose that spacetime itself is not fundamental at all, but an illusion generated by something deeper. What these diverse approaches share is the recognition that the Planck length marks a limit to the classical, intuitive notion of distance. Another way to understand this is through the principle of dimensional analysis. The constants used to define the Planck length, Gg, Hh, Cc, are not chosen arbitrarily. They are the fundamental knobs of nature. One governs quantum uncertainty, one governs gravitational strength, one governs the conversion between space and time. Any theory that attempts to describe space-time at the smallest scales must involve all three. This makes the Planck length a natural scale, a length that physics itself provides, rather than one we invent. It is not introduced to fix a problem in a calculation. It emerges unavoidably from the structure of the theories. This also explains why smaller lengths do not naturally appear in established physics. There is no known mechanism, no force, no particle, no field that would allow space-time structures to be probed meaningfully below this scale. Any attempt to do so runs into the same fundamental obstacle. Energy concentration inevitably leads to gravitational collapse. The Planck length, therefore, acts as a conceptual boundary. It does not tell us what spacetime is made of. It tells us where our current descriptions, however successful, stop making coherent sense. This boundary should not be confused with certainty. Physics has encountered apparent limits before that were later reinterpreted or bypassed. What makes the Planck length different is that it arises from combining two theories that have each been tested to phenomenal precision in their own domains. It is not an artifact of incomplete data, but of theoretical consistency. That said, caution is essential. The Planck length is a guide, not a measurement. It points to where new physics is required, but it does not specify what the physics must look like. Treating it as a literal, rigid, smallest unit of space risks overstating what we know. What can be said with confidence is this: if spacetime becomes quantum in any operational meaningful sense, it is expected to occur at or near the Planck length. That is where quantum uncertainty, gravitational interaction, and spacetime structure converge. Above this scale, smooth geometry works extremely well. Below it, the distance itself becomes an unstable concept. The language of points, lengths, and intervals begins to lose its physical grounding. This makes the Planck length a crucial turning point in our discussion. It provides a specific, numerically defined scale at which questions about quantum spacetime become unavoidable rather than speculative. The next step is to consider the companion to length, time. Time is usually treated as the most reliable ingredient in physical description. Events occur, time passes, and the order of cause and effect feels absolute. Even when space is curved or distorted, time still appears to provide a steady sequence, a universal metronome in which physics unfolds. Classical mechanics depends on this assumption, and even general relativity, for all its flexibility, preserved a continuous, smooth notion of duration. And if distance can reach a limit where the idea of length loses meaning, it is reasonable, even necessary, to ask whether time faces a similar constraint. The temporal analogue of the Planck length is known as the Planck time. It is defined as the time light would take to travel one Planck length in a vacuum. Planck length divided by the speed of light. Like its spatial counterpart, it is constructed by combining g, h, and c. It does not arise from experiment, but from the same demand for consistency between our great theories. Numerically, the Planck time is on the order of 10 to the power of minus 4310 to the power of minus 43 seconds. This is not merely small by human standards, it is vastly smaller than any time interval that could be measured, produced, or resolved by any known physical process. Its significance lies not in its unimaginably tiny value, but in what it represents. In everyday physics, we assume time intervals can be made shorter by using faster clocks or more energetic processes. Atomic clocks measure time using oscillations within atoms, reaching extraordinary precision. Particle physics experiments probe interactions occurring over intervals as short as 10 to the power of minus 25 to 10 to the power of minus 25 seconds. In all these cases, time behaves as a continuous parameter that can, in principle, be subdivided further as technology improves. Quantum mechanics complicates this picture by linking time and energy through the uncertainty principle. Processes that occur over very short durations involve large uncertainties in energy. This is not a limitation of instruments. It is a fundamental feature of quantum systems. Shorter time intervals require higher energies to resolve meaningfully, and on its own this does not imply a minimum time. Standard quantum mechanics allows for arbitrarily short intervals. The profound difficulty appears when gravity is included. High energy densities distort spacetime. This is the central insight of general relativity. Energy and momentum determine how spacetime curves. If an attempt is made to probe a time interval comparable to the Planck time, the energy required becomes so enormous that it strongly affects the geometry of spacetime itself. At that point, the concept of a sharply defined time interval, a clear separation between one moment and the next, begins to fail. Just as with distance, the measurement process undermines itself. The physical process used to define the interval alters the spacetime structure in which the interval is being defined. The notion of a clean, universal tick becomes unstable. This instability has deep consequences for causality. Causality depends on the unambiguous ordering of events. One event causes another if it precedes it in time, and can influence it through some physical process. General relativity refines this idea by tying causal structure to spacetime geometry through light cones, which define which events can influence which others. Even in curved spacetime, causal order remains locally well defined. However, at extremely small timescales approaching the Planck time, this structure becomes uncertain. If spacetime itself fluctuates due to quantum effects, then the light cones that define causal relationships also fluctuate. The clear classical distinction between before and after can blur. This does not mean that causality disappears in any everyday or even astrophysical sense. It means that the classical notion of sharply ordered time intervals may not apply at the smallest conceivable scales. Cause and effect may still exist, but not in a form that maps cleanly onto a smooth, continuously flowing time parameter. This issue becomes especially critical when considering the early universe. Cosmological models based on general relativity describe an expanding universe that was denser and hotter in the past. As we trace this expansion backward, time intervals shrink and energy densities rise catastrophically. Eventually, the equations predict a state of infinite density at t equals 0, the classical Big Bang singularity. Near this beginning, the timescales involved approach the Planck time. In this regime, So classical spacetime cannot be assumed to exist in its usual form. Quantum fluctuations in geometry would have been unavoidable, dominant. This does not mean the universe began at a specific instant in the classical sense. It means the concept of time itself may not extend meaningfully beyond a certain point. Asking what happened before the Planck time may be like asking what lies north of the North Pole. The question assumes a linear, continuous temporal structure that may no longer apply. Importantly, the Planck time should not be interpreted as the smallest tick of a universal clock. There is no evidence, and many theories of quantum gravity do not predict, that time advances in discrete steps of this duration. Instead, the Planck time marks a boundary for classical description, and it identifies the scale at which treating time as a smooth continuous parameter ceases to be justified without a radical modification of physics. Above this scale, time behaves in ways that align perfectly with both experience and experiment. Clocks can be synchronized. Durations can be compared. Cause and effect are ordered. Below it, the assumptions underlying these concepts are no longer secure. This mirrors what we saw with distance. The Planck length does not prove the space is made of indivisible units. It indicates the concept of distance loses operational meaning below a certain scale. The same applies to duration. Time, like space, may be emergent. It may arise from more fundamental processes that only approximate continuity when viewed at large scales. At the very smallest scales, then the language of moments and intervals may not correspond to anything physically real. This perspective helps reconcile why time works so flawlessly in classical and relativistic physics. It is not because time is fundamental in all regimes, but because it is an effective concept that applies where quantum fluctuations are negligible and geometry is stable. Recognizing a limit to classical duration does not undermine physics. It clarifies its scope. It explains why attempts to describe the earliest universe or the interior of black holes encounter conceptual breakdowns rather than smooth extrapolations. The Planck time, therefore, serves as a marker. It signals where familiar notions of time reach the edge of their usefulness. Beyond that edge, new descriptions are required, not because time vanishes, but because the classical idea of duration no longer applies. Together, the Planck length and Planck time reinforce a consistent and humbling picture. Smooth space-time with its continuous distances and durations is an excellent, empirically verified description at all accessible scales. At sufficiently small scales we may never directly observe, both space and time may require a different foundation. The breakdown of continuity is not an anomaly, it is a clue. It points toward a deeper structure in which space-time, as we usually understand it, emerges only when viewed from far enough away. And if space-time is not fundamental, then what appears to us as emptiness, the vacuum, must be re-examined. At these extreme scales, the idea of an empty, featureless void no longer holds. So what appears as nothingness in classical physics becomes seethingly active in quantum theory. Even in the absence of particles, space is not truly empty. It is filled with fluctuations that arise from the basic structure of quantum mechanics. These are known as quantum vacuum fluctuations. In quantum field theory, fields exist everywhere, permeating all of space-time even where no particles are present. Each field possesses a minimum amount of energy, called the zero-point energy. This energy cannot be removed. It is not associated with motion, heat, or radiation in the usual sense. It is a direct consequence of the Heisenberg uncertainty principle inherent in quantum systems. A useful, though simplified way to understand this is to consider that quantum fields cannot be perfectly still. Just as a particle cannot have both a perfectly defined position and momentum, a field cannot have both exactly zero energy and a perfectly fixed configuration. As a result, even the lowest possible energy state, the vacuum, involves constant fleeting fluctuations. These fluctuations are not merely mathematical artifacts, they have observable, measurable consequences. One famous example is the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience a subtle but measurable attractive force. This force arises because the quantum vacuum fluctuations between the plates are restricted compared to those outside, creating a pressure difference. Another is the spontaneous emission of light by excited atoms, which occurs because the vacuum itself is not static, but can stimulate emission. In most contexts, these effects are extremely small, subtle whispers of the underlying quantum nature. They average out and have negligible influence on large-scale behavior. But when gravity is considered, the situation changes dramatically. General relativity teaches that all forms of energy influence space-time geometry. Any form of energy, including the zero-point energy of the quantum vacuum, contributes to curvature. If quantum fields fluctuate, then the energy density associated with those fluctuations should also fluctuate. And if energy fluctuates, space-time geometry should, according to general relativity, respond. This leads to a striking, inevitable possibility. At very small scales, space-time itself may fluctuate. Instead of being a smooth, fixed geometric structure, space-time may exhibit constant, rapid variations in curvature. The distances and angles would not be fixed. They would shift and blur due to underlying quantum effects. The classical picture of a stable, silent background would no longer apply. This revolutionary idea was explored in depth by John Wheeler, the physicist who coined the term black hole and made major contributions to both general relativity and quantum theory. Wheeler recognized that if quantum mechanics applies to everything else in nature, it should also apply to space-time itself. He proposed that at extremely small scales, near the Planck length, space-time might be wildly irregular. He described this hypothetical regime as quantum foam. The term is metaphorical, but it conveys an essential point. Just as foam consists of bubbles constantly forming, merging and collapsing, quantum spacetime might involve the constant, so probabilistic creation and annihilation of tiny geometric features, miniature wormholes, virtual black holes and fluctuations in connectivity. Tiny distortions, tunnels or twists could appear and disappear on timescales of the Planck time. It is important to be clear about what this picture does and does not claim. Quantum foam is not a confirmed description of reality. It is a conceptual image, a visualization meant to capture the idea that space-time may not be smooth when examined with a hypothetical Planck-scale microscope. The details depend entirely on the correct theory of quantum gravity, which we do not yet have. Nevertheless, the concept serves a vital role. It provides a way to imagine how smooth space-time might break down, without invoking literal rigid discreteness or sharp boundaries. In this view, space-time is not made of solid blocks. Instead, it is more like a restless, churning medium whose average behavior over larger scales appears smooth, while its microscopic behavior is highly irregular, even chaotic. The scale at which this foam-like behavior becomes relevant is, of course, near the Planck length and Planck time. At these scales, quantum fluctuations of energy are so strong that they produce significant wild fluctuations in curvature. The geometry of spacetime would no longer be well-defined in the classical sense. It would be a probabilistic superposition of many possible geometries. This does not mean that spacetime dissolves into chaos in any observable macroscopic way. These fluctuations would be confined to scales fantastically smaller than anything we can directly access. At larger scales, then the fluctuations would average out to zero, producing the smooth, predictable geometry described by general relativity. This averaging process is central to why classical spacetime works so well. Just as the frantic thermal motion of atoms produces a smooth, stable temperature at human scales, quantum fluctuations of spacetime could produce smooth geometry when viewed from far enough away. The idea of quantum foam also highlights why measurement becomes so problematic at these scales. If space-time itself is fluctuating, then the concept of a fixed ruler or a perfect clock becomes problematic. Any measuring device would itself be embedded in and made of the same fluctuating geometry it is trying to measure. Thus, this completely undermines the classical assumption that distances and durations can be defined independently of the measurement process. Instead, geometry becomes relational and context-dependent. What can be said about distance depends on how the system is probed, and the probe itself is part of the quantum system. Wheeler emphasized that this regime is not one where familiar intuition should be trusted. Concepts such as points, trajectories, and continuous paths, the bedrock of classical physics, may no longer apply. The mathematics of smooth manifolds may fail because the underlying structure does not support it. At the same time, it is crucial to avoid overstating the implications. Quantum foam does not imply that spacetime is literally boiling or unstable in any macroscopic sense. Though it does not mean spacetime is tearing itself apart on scales that could affect atoms, people, or planets. The effects are confined to scales where our classical language and intuition break down. From a physical standpoint, quantum foam represents a region of theoretical overlap where known principles intersect but do not yet yield a complete description. Quantum mechanics predicts fluctuations. General relativity predicts that energy affects geometry. Combining these predicts fluctuating geometry but does not yet provide a complete self-consistent theory. Different approaches to quantum gravity treat this situation differently. Some predict discrete geometric structures, others predict smooth but wildly fluctuating geometries, and some suggest spacetime emerges from entities that are not geometric at all. What unites these approaches is the rejection of smooth spacetime as a fundamental assumption at all scales. Instead, smoothness becomes something that emerges when fluctuations are averaged over large distances and long times. The imagery of quantum foam helps bridge the gap between abstract theory and physical intuition. It allows us to think of spacetime not as a static stage, but as an active participant, subject to the same quantum rules that govern everything else. This shift in perspective is significant. Once spacetime is allowed to fluctuate, it becomes clearer why attempts to quantize gravity face such severe difficulties. The object being quantized is not a field within spacetime, but spacetime itself. It also clarifies why classical geometry reappears so reliably at our scales. The foam does not disappear, and it simply becomes irrelevant when we average over it, and a stable geometry crystallizes out. In that sense, quantum foam is not a competing description of spacetime. It is a candidate for what lies beneath it. Whether this picture is correct remains an open question. What matters here is the role it plays in thinking about quantum spacetime. It provides a concrete, if metaphorical, way to imagine how continuity might fail without abandoning physical realism. Spacetime in this view is neither perfectly smooth nor fundamentally broken into blocks. It is structured in a way that depends profoundly on scale. At large scales, it behaves like a continuous geometric entity. At the smallest scales, it may be dominated by quantum fluctuations that defy classical description. This non-smooth microscopic picture marks a transition in our discussion. The focus shifts from whether spacetime can be treated as smooth to what might replace smoothness when it cannot. The language necessarily becomes more tentative here, not because physics becomes speculative, but because our current tested theories reach their limits. What can be said with confidence is limited but not trivial. Quantum fluctuations of spacetime offer a coherent, plausible reason why smooth geometry should fail at small scales while remaining accurate at large ones. They connect quantum uncertainty, gravitational response, and the emergence of classical spacetime into a single conceptual framework. This does not provide a final answer. It provides a direction. It suggests that spacetime's quantum nature, if it exists, that is not static or discrete in a simple sense, but dynamic, relational, and scale-dependent. The imagery of foam may not survive future, more complete theories. The underlying insight that smoothness is emergent likely will. The phrase quantum foam is often the first vivid image people encounter when imagining space-time at the smallest scales. It suggests motion, instability, and complex structure where classical physics expects only smooth, featureless geometry. As an idea, it is powerfully evocative. As a literal description, it can be misleading if not handled with care. Understanding what the term is meant to convey and what it is not is essential. At its core, quantum foam is an attempt to describe what spacetime might be like when quantum effects on gravity become unavoidable, and it arises from combining two well-established facts. Quantum mechanics predicts unavoidable fluctuations in energy, and general relativity predicts that energy affects spacetime geometry. If both statements are taken seriously, then spacetime geometry itself should fluctuate at sufficiently small scales. That conclusion is conceptually straightforward. Visualizing it is not. The human mind tends to picture space as an empty container and time as a flowing sequence. Foam suggests bubbles forming and popping within that container. This is not what is meant. In Wheeler's vision, there is no pre-existing smooth background space in which the foam sits. The fluctuations are not happening in space-time, they are fluctuations of space-time. This distinction is everything. When John Wheeler introduced the term, he was not proposing a specific physical structure. He was pointing to a regime where classical geometric language, points, lines, continuous surfaces, breaks down. The foam metaphor was meant to signal the loss of smoothness and deterministic predictability, not to specify the exact form of what replaces it. At extremely small scales, the quantities that define geometry in general relativity, distance, angle, curvature, may not have stable single values. Instead of one well-defined geometry, there may be a vast probabilistic superposition of many possible geometries, each contributing to the overall quantum state. In that sense, spacetime would behave more like a quantum system, with amplitudes and probabilities, than a classical object with definite properties. The word foam captures this multiplicity and ceaseless change. But it is a metaphor, not a model. Metaphors are useful because they allow unfamiliar, radical ideas to be discussed using familiar language. They are dangerous when taken too literally. Quantum foam does not imply literal bubbles of space popping in and out of existence in any simple, observable way. It does not imply turbulence or motion that could be detected by an instrument. It does not imply large-scale instability. The foam, if it exists, would be confined to scales far smaller than anything that could influence ordinary physics or astronomy. One way to keep this grounded is to remember that the foam is not primarily a claim about appearance. It is a claim about calculation. When physicists attempt to describe spacetime using quantum principles, the mathematics suggests that the path integral and some overall possible histories must include contributions from wildly different non-classical geometries. The smooth geometry of general relativity appears only as a dominant classical approximation, an average over these myriad possibilities. In this sense, the foam is statistical rather than mechanical. It is not a substance. It is a way of talking about the fundamental uncertainty and fluctuation inherent in a quantum description of geometry. This also explains why visualization is so limited. Human intuition is built around objects moving through space over time. Quantum foam challenges both ideas at once. There may be no fixed objects, no stable background, and no single universal timeline in the deep quantum regime, and any mental picture that resembles familiar physical scenes is likely to mislead. This is why careful, precise language is so important. Saying spacetime is foamy does not mean it is chaotic in an everyday sense. It means that classical descriptions fail to capture its behavior at a Planck scale resolution. It also means that different, competing theories of quantum gravity can use the same metaphor while meaning radically different things. In some approaches, spacetime is fundamentally discrete. In others, it is continuous but subject to enormous quantum fluctuations. In still others, spacetime emerges from entities that are not geometric at all. All of these might be loosely described as involving quantum foam, but they are not equivalent. The metaphor unifies them only at a very high, almost poetic level. This is where the boundary between established principles and theoretical speculation becomes most evident. Quantum foam has not been observed. There is no experimental evidence that directly confirms or rules out its existence. Its status is theoretical, inferred from the compelling attempt to reconcile quantum mechanics with gravity. That makes it a plausible, well-motivated idea, not an established fact. Acknowledging this is not a weakness. It is a strength. Physics progresses by clearly distinguishing what is known, what is inferred, and what is purely unknown. What is known is that quantum fields fluctuate. What is known is that energy affects spacetime geometry. What follows from combining these facts depends on the assumptions about how quantum principles apply to spacetime itself. That is precisely where different, full-fledged theories of quantum gravity diverge. The foam metaphor helps prevent another kind of misunderstanding. The idea that spacetime must be either perfectly smooth or completely broken into rigid Lego-like pieces. The reality may be more subtle, more alien. Spacetime may lack a fixed classical structure at small scales without being composed of simple building blocks. This middle ground is difficult to describe without imagery, which is why metaphors persist despite their limitations. Another vital point is that quantum foam does not imply randomness without structure. Quantum mechanics is probabilistic, but it is not arbitrary or lawless. Probabilities follow precise, elegant mathematical rules. If spacetime fluctuates quantum mechanically, those fluctuations would also follow well-defined laws, and even if individual outcomes are not deterministic, from this perspective, foam does not mean disorder. It means indeterminacy constrained by physical principle. The usefulness of the concept lies in how it reframes our expectations. Instead of assuming spacetime must remain smooth at all scales, it allows for the possibility that smoothness is an emergent property. Instead of expecting a single definitive geometry, it allows for a superposition of many possible geometries contributing collectively to what we perceive. This prepares the conceptual ground for more formal mathematical approaches. Once the metaphor has done its job of loosening our classical intuitions, it must be set aside. Real progress depends on precise mathematical frameworks, not imagery. The foam is a bridge, not a destination. It also serves as a caution. And overly concrete images can create false confidence. Thinking of spacetime as frothy or bubbling can make the profoundly unknown feel familiar when it is not. The goal here is not comfort, but clarity. In summary, quantum foam is best understood as a conceptual signal. It marks the anticipated breakdown of smooth spacetime at very small scales. It captures the profound idea that geometry itself may be subject to quantum uncertainty. It does not specify the detailed structure of spacetime, nor does it claim direct observability. Treating it as a metaphor keeps it useful. Treating it as a literal picture leads to confusion. With that distinction firmly in place, our attention can shift toward the serious, detailed theories that attempt to describe quantum spacetime without relying solely on imagery. The foam has served its purpose by challenging classical assumptions. What comes next requires more precise tools. One major serious attempt to reconcile quantum mechanics with gravity begins by taking general relativity utterly at face value. Instead of treating gravity as a force to be added to quantum field theory, this approach starts with spacetime itself and asks how its geometry might behave if quantum principles are applied directly to it. This line of thought has crystallized into a framework known as loop quantum gravity, LQG. The central idea behind LQG is straightforward in spirit, even if the mathematics is demanding. If spacetime is dynamic, as general relativity insists, and if quantum mechanics applies universally, then spacetime geometry itself should be subject to quantization. Distances, areas, and volumes should not vary continuously without limit, but should come in discrete quantized amounts. This approach does not attempt to unify all forces of nature. It does not introduce extra dimensions or new particles beyond those already known. Its goal is narrower but deeper, to construct a quantum theory of space-time geometry and gravity alone. Two physicists most closely associated with the development of this framework are Carlo Rovelli and Lee Smolin. Working independently and collaboratively from the late 1980s onward, they helped shape its mathematical structure and clarify its physical interpretation. One of the key conceptual moves in LQG is the complete abandonment of a fixed background spacetime. This choice aligns the theory intimately with the background independence of general relativity. There is no predefined geometry on which quantum processes unfold. Instead, geometry is part of the quantum system. This makes LQG a background-independent quantum theory. Spacetime does not exist first, with quantum effects layered on top. Geometry emerges from the quantum states themselves. To describe these states, the theory introduces a profoundly new way of representing geometry. Instead of smooth metric fields defined at every point, geometry is encoded in networks of discrete elements known as spin networks. A spin network is not a physical object embedded in space. It is an abstract mathematical graph that represents the quantum relationships between elementary chunks of geometry. The nodes of the network correspond to elementary volumes. The links connecting nodes correspond to elementary surfaces. Together, they define a quantum state of geometry. Each link carries a Senel quantum number, hence the name, that determines the area of the surface it represents. Each node carries information about the volume of the region. These geometric quantities are not continuous. They take on discrete quantized values, much like the energy levels of an atom. This leads to one of the most striking predictions of loop quantum gravity. Geometric quantities have minimum non-zero values. There is a smallest possible area and a smallest possible volume. Space, in this precise sense, is not infinitely divisible. It is crucial to state this carefully. The discreteness here does not mean that space is made of tiny cubes arranged on a rigid grid, like a chessboard. The geometry is relational and topological rather than lattice-like. The spin network defines how volumes connect to each other via shared surfaces. It does not sit in an already existing space. It defines space. At large scales, when a vast number of these elementary quanta are woven together, the discrete structure becomes indistinguishable from a smooth continuum. The familiar geometry of general relativity emerges as an approximation, just as the smooth flow of water emerges from the chaotic motion of countless molecules. This emergence is central to the credibility of the theory. Any viable approach to quantum gravity must reproduce classical spacetime at scales where general relativity has been tested. LQG is constructed so that this limit exists in principle, though demonstrating it in full, rigorous detail for all situations remains an active and challenging area of research. And time is treated in an equally radical way. In LQG, there is no single universal time parameter flowing in the background. Instead, change is described relationally. Physical quantities evolve with respect to one another rather than with respect to an external clock. This reflects a deep lesson already present in general relativity. Time is not an absolute background variable. It is tied to the geometry and matter content of the universe. LQG extends this idea fully into the quantum domain. One consequence is that the theory does not predict spacetime foam in the wildly fluctuating, pictorial sense often imagined. Instead of a chaotic, lawless froth at every scale, the theory predicts a granular but well-defined quantum structure. The quantum uncertainty lies in which spin network configuration describes a given situation, a superposition of possible geometries, not necessarily in the violent instability of a given geometry. This distinction matters. LQG suggests spacetime has a definite, though discrete, quantum structure, governed by precise mathematical rules. These rules lead to specific, tantalizing predictions. One of the most studied concerns the fate of classical singularities. In simplified, symmetric models, like those describing the very early universe or the center of a black hole, LQG equations replace the classical singularity with a finite, well-behaved quantum state. Instead of infinite density, the theory predicts a quantum bounce or a transition through a minimum finite volume. Applied to cosmology, then this leads to scenarios like loop quantum cosmology, where the classical Big Bang is replaced by a big bounce. The universe contracts from a previous phase to a very small but finite minimum size, then expands again into our familiar universe. Time does not begin at a singularity. The classical description simply ceases to be valid, giving way to a quantum regime. It is important to be clear about the status of these results. They are derived within simplified, symmetry-reduced models that capture key features of the full theory, but do not yet represent complete generic solutions. They demonstrate consistency and conceptual possibility rather than providing final, certain answers. Another area of intense interest is black hole physics. LQG predicts that the area of a black hole's event horizon is quantized, coming in discrete steps proportional to the square of the Planck length. This provides a potential microscopic explanation for black hole entropy, the famous Bekenstein-Hawking formula S equals A over 4S equals A over 4, connecting geometric degrees of freedom to thermodynamic behavior. Here again, the results are suggestive and promising, showing that the theory can reproduce known semiclassical results while offering a new geometric origin for them. Despite these intriguing successes, loop quantum gravity faces significant challenges. The mathematics is formidably complex. Connecting the discrete quantum geometry to smooth spacetime in all general situations is technically arduous. Making direct contact with experiment is profoundly difficult because the predicted effects become significant only at the Planck scale, far beyond the reach of any conceivable particle accelerator or astronomical observation. There is also the question of completeness. LQG focuses primarily on quantizing spacetime geometry and gravity. It does not automatically incorporate the other fundamental forces, electromagnetism, weak and strong nuclear forces, or the particles of the standard model. Whether and how these can be included in a unified way remains an open, active problem. These limitations are openly acknowledged by researchers in the field. They are not viewed as failures, but as honest indicators of how profoundly difficult the problem of quantum gravity truly is. What gives loop quantum gravity its standing as a serious candidate theory is not that it provides all the answers, but that it is built on clear but principled foundations. It respects the background independence of general relativity, it applies quantization to geometry itself, and it produces concrete mathematical predictions, even if they are currently untestable. Equally important is what the theory does not assume. It does not rely on extra spatial dimensions. It does not require unobserved symmetries or new particles. It does not posit a pre-existing space-time arena. Everything begins with the dynamical geometry we already know from Einstein and asks how it behaves under quantum rules. This makes LQG conceptually conservative in its ingredients, even as it is mathematically radical in its formulation. Its picture of spacetime is neither perfectly smooth nor wildly fluctuating in a foam-like sense. It is discrete, relational, and structured. Her smoothness emerges only when a vast number of quantum geometric elements are considered together. This offers one clear, concrete answer to our central question. In this approach, spacetime is always quantum. What changes with scale is whether that quantum nature is visible or hidden by coarse graining. At large scales, quantum geometry looks classical. At the Planck scale, its discreteness becomes fundamental. Loop quantum gravity does not claim to be the final word. It claims to be a consistent step. It shows that it is possible to construct a rigorous theory in which spacetime itself is quantized without abandoning the core insights of general relativity. Whether this approach is correct remains unknown. What it provides is a concrete example of how the smooth spacetime of experience might arise from a deeper quantum structure, and how continuity could fail without descending into incoherence. In doing so, it sets a standard of mathematical rigor and conceptual clarity against which other approaches can be compared. Another major attempt to understand quantum spacetime begins from a diametrically different starting point. Rather than quantizing spacetime geometry directly, this approach asks whether we have correctly identified the basic ingredients of reality in the first place. Perhaps the problem lies not with gravity, but with our point-like conception of particles. This line of thought leads to string theory. The core premise of string theory is simple to state, revolutionary in implication. The fundamental constituents of nature are not zero-dimensional point particles, but exceedingly tiny, one-dimensional vibrating strings. These strings are fantastically small, with a characteristic length scale close to the Planck length. They can vibrate in different modes, much like the strings of a violin. Each distinct pattern of vibration corresponds to a different particle with its own mass, charge, and spin. In this picture, particles such as electrons, quarks, photons, and even gravitons are not fundamentally distinct entities. They are different notes played on the same type of fundamental string. What appears as particle diversity at low energies is a unified harmony at the smallest scales. This idea emerged gradually in the late 20th century, originally as a theory of the strong nuclear force, before it was realized that its most compelling feature was a natural inclusion of gravity. Physicists searching for a consistent quantum theory of gravity found that the standard point-particle approach led to fatal infinities. String theory offered a way around this by softening the short-distance behavior of interactions. Point particles interact at a single infinitesimal location, leading to sharp, uncontrollable divergences in calculations. Strings, by contrast, have spatial extent. Interactions are spread out along the string's length, which smooths out the behavior at extremely short distances, effectively smearing the interaction over a tiny volume. This mathematical feature turns out to be crucial. One of the most profound results of string theory is that gravity is not added by hand, it appears naturally. Among the possible vibrational modes of a closed string, there is one that behaves exactly like a massless, spin-2 particle, the precise properties expected for the quantum carrier of gravity, the graviton. In other words, a consistent quantum description of gravity emerges automatically, inevitably, from the theory. This was a major motivation for pursuing the framework further. A single theoretical structure seemed capable of incorporating both quantum mechanics and gravity in a consistent way, something no point-particle theory had achieved. The ambition of string theory, however, goes far beyond just fixing gravity. Its broader goal is unification. It aims to describe all fundamental forces and all matter particles within a single coherent mathematical framework. Electromagnetism, the weak and strong nuclear forces, and gravity would all arise from the dynamics of vibrating strings. Though this grand unifying ambition has shaped a vast portion of theoretical physics over the past several decades. Large international communities of researchers have explored the intricate mathematical structure of string theory, often working in close dialogue with developments in particle physics, cosmology, and pure mathematics. The research culture surrounding it is deeply integrated with high-energy physics. Ideas developed in string theory circulate through institutes and collaborations worldwide, influencing how fundamental questions are framed, even when direct tests remain elusive. One of the most striking and controversial features of string theory is that it requires more dimensions of space than the three we experience. In its most consistent formulations, string theory requires a total of 10 spacetime dimensions, 9 of space and 1 of time. Some versions, M theory, require 11. This immediately raises an obvious question. If extra dimensions exist, why don't we see them? The standard answer is compactification. These extra dimensions are imagined to be curled up or compactified into extremely small complex shapes, like Calabi-Yau manifolds, with sizes on the order of the Planck length. At human atomic or even particle accelerator scales, these dimensions are effectively invisible. One would need a Planck energy probe to resolve them. An often used but limited analogy is a garden hose. From a distance it looks like a one-dimensional line, but up close its circular cross-section, a second dimension, becomes apparent. Similarly, and every point in our three-dimensional space could hide a tiny six-dimensional geometric shape. It's important not to take this analogy too literally. The mathematics of compactification is highly sophisticated, involving complex geometry and topology. Conceptually, what matters is that spacetime in string theory is richer and more intricate than the three-dimensional expanse of our daily lives. These extra dimensions are not optional. They are required for the mathematical consistency of the theory, for the cancellation of certain quantum anomalies that would otherwise render it nonsensical. In string theory, space-time itself is not fundamentally quantized in the same discrete manner as in loop quantum gravity. Instead, the smoothness of space-time is preserved, but the nature of the fundamental objects within it, the strings, modifies physics at the short distances. The extended nature of strings smears interactions, preventing the formation of the point-like singularities that plague point-particle quantum gravity. In this sense, string theory addresses the problem of quantum spacetime indirectly. It does not begin by discretizing geometry. It modifies the behavior of matter and forces so that spacetime remains well-behaved, smooth, and continuous even at the smallest scales. This leads to a different intuition. Rather than spacetime fragmenting into discrete chunks, spacetime remains a smooth manifold, but the physics occurring within it is softened at Planckian distances. Singularities are avoided not by quantizing geometry, but by changing the nature of the interacting entities. This distinction is crucial when comparing approaches. Loop quantum gravity predicts discrete geometric quantities. String theory predicts smooth geometry with new, extended fundamental degrees of freedom that prevent its breakdown. Both aim to resolve the same fundamental conflict, but they do so based on different starting assumptions. String theory also introduced powerful transformative ideas like duality. Different-looking string theories, defined in different numbers of dimensions or with different parameters, can turn out to be mathematically equivalent, different faces of the same underlying theory. One profound example of this is the ADS/CFT correspondence anti-de Sitter/conformal field theory. Discovered by Juan Maldacena in 1997, this is a concrete realization of the holographic principle, and it proposes a precise equivalence between a string theory describing gravity in a certain higher dimensional spacetime anti-de Sitter space, and a quantum field theory without gravity living on its lower dimensional boundary. This suggests, staggeringly, that spacetime geometry and gravity in the bulk can emerge from a non-gravitational quantum system on the boundary. Distance and volume could be derived, collective concepts rather than primitive ones. This has led some physicists to suggest that in string theory, spacetime itself is not fundamental. Instead, it arises from more fundamental, non-geometric degrees of freedom, like quantum entanglement patterns in a lower dimensional system. In that view, asking, when does spacetime become quantum, might be asking the wrong question. That spacetime may be an effective concept that only appears under certain conditions, emerging from a quantum reality that is not spatiotemporal at all. Despite its mathematical beauty and unifying power, string theory faces serious, well-known challenges. The most significant is testability. The characteristic scales at which stringy effects become important are near the Planck scale, placing them far, far beyond the reach of any current or foreseeable experiment. No direct experimental evidence yet confirms the existence of strings or extra dimensions. There is also the issue of landscape and predictivity. String theory does not produce a single, unique description of our universe. It allows an enormous number, perhaps 10,500, 10,500 or more, of possible stable configurations, vacua, each corresponding to different physical constants, particle properties, and even up to numbers of observable dimensions, explaining why our particular universe has the specific finely tuned properties we observe becomes a major puzzle. Supporters argue this flexibility may reflect the true complexity of fundamental physics and might connect to the multiverse concept in cosmology. Critics argue that without unique predictions for observable low-energy physics, the theory risks becoming detached from empirical science. These debates are active and ongoing. They are part of what makes string theory both enormously influential and deeply controversial. What matters for our question is not whether string theory is ultimately correct, but what it demonstrates. It shows that there are multiple radically different, yet internally coherent ways to approach the problem of quantum spacetime. One can attempt to quantize geometry directly, L, Q, G, or one can modify the nature of fundamental objects so that geometry remains smooth, string theory. String theory occupies this second path. It offers a vision in which spacetime does not fragment or fluctuate wildly at small scales in a geometric sense. Instead, the violent infinities that plague point-particle theories are avoided, because interactions are fundamentally smeared. Geometry remains continuous, but its meaning and perhaps its very fundamentality are called into question by deeper holographic principles. This broadens the theoretical landscape immensely. It shows that quantum spacetime does not have a single obvious form, different. Well-motivated starting assumptions lead to different pictures, each mathematically sophisticated and grounded in different aspects of established physics. In that sense, string theory complements rather than replaces other approaches. It provides a contrasting, equally ambitious answer to the same underlying question. How can quantum mechanics and gravity coexist? Whether spacetime becomes quantum through discreteness, through emergence, or through being rendered soft by extended objects remains unresolved. String theory shows that smooth spacetime might survive at all scales as a good description, not because it is fundamental, but because the fundamental objects within it are extended. This perspective does not settle the issue, it deepens it. By offering a radically different route, our string theory forces us to ask our question more carefully. What exactly do we mean by space-time becoming quantum? Is it the geometry that changes, or the entities that give geometry its meaning? These questions remain open, a testament to the depth of the mystery. What is clear is that string theory has permanently reshaped how physicists think about space-time, scale, and unification. Even if it does not describe nature directly, its influence on the search for quantum gravity is undeniable. It stands as a towering reminder that the path from smooth spacetime to quantum reality may not be singular, and that the correct description may lie in a realm deeper than geometry itself.